Okay, so good morning, everyone. Today we will have Jinho Lee, assistant professor at Seoul National University for the talk, and he will host the talk about GPU acceleration, specifically for genomic sequence alignment. So thanks a lot, Professor Lee, for being here with us. I give you the stage now. Thank you.
Okay, yeah, thanks so much for having me here. I just had a walk on the campus, like beautiful campus. And I talked a lot about this, but yeah, beautiful weather.
Yeah.
Okay, thanks, Alex. Thank you so much again for having me here. So the talk is more about GPU acceleration than genomics. But I'm still trying to understand this application. Well, I still don't. So I barely understood it just enough to accelerate using GPUs, and still learning. So here's me. Okay. Yeah, in case you're watching this on the video, yeah, this is a photo of me. So I spent 11 years from bachelor's to PhD on SNU and moved to US, worked at IBM for about 4 years, and then came back to Seoul to become a professor. So that's what I'm doing right now. I usually work on computer architectures and softwares. Usually on novel architectures. And before going into the real topic, this is a kind of topics that I work on. Of course, there are multiple applications we work on computer systems. Well, what I brought is, of course, excuse me, the pen should be working. Yep, genomics, neural networks, graph processing, which are all my favorite applications. And then there are always people building accelerators for their favorite application domains. Then you're usually not satisfied with a single chip, so you build a server comprising many of those. You're probably used to machines with multiple GPU cards these days. And then if you're still not satisfied with that, you usually build a cluster. So on those, I work on quantization of neural networks and graph processing and how graph representation, that kind of things. And then I also work on neural processing unit architectures and processing in memory, both on the pure architectures, FPGAs, or even trying to fabricate a chip in the near future. Then I also work on software optimizations for CPUs and GPUs. And I also work a little bit on large-scale model training. And among those, of course, what I want to talk about today is on software optimization, especially for the GPU. All right, like I just said, I am not so much of an expert on genomics itself, but I know I have been studying over the past 5 years on how to accelerate them using GPUs. So genomics usually starts with what's called a sequence alignment. So if you have a sequencing machine, then it reads the DNA molecule and creates multiple of shorter pieces called reads, where the human genome is usually a few billions in each length, but a read usually spans somewhere between 100 base pairs to maybe a couple of thousands. So from those small reads, you're supposed to build, to reconstruct the whole genome sequence, and that is through a procedure we call sequence alignment. Luckily, we have a reference genome for humans, so we try to perform a approximate stream matching, such that they fit. Such that after a sequence alignment, we kind of know which one fits where. And this is a software procedure, and unfortunately, this is becoming a huge bottleneck on modern computing systems. Primarily because the sequencing procedure itself is becoming faster and cheaper. And people say that the sequencing procedure is rapidly growing much faster than the Moore's law. And we know that the Moore's law is half that anyway, but still the sequencing procedure is growing much faster than the Moore's law. And for that, if you need acceleration and if the application is still running on CPUs, we try to use GPUs on a project popular for many computer science people. So there are many genomics pipelines, and as far as I know, 2 of the algorithms are most popular. One is BWMAP, and the other is MIMAP2. Also, one is for relatively short reads, spanning for a couple of hundred base pairs. And the other is for other minimap 2 is for longer arrays spanning for a couple of thousands of base pairs. So unfortunately, they both run on CPUs, and it's becoming very hard to keep up with the speed of modern sequencing machines. So because of that, our goal was to accelerate them using GPUs. And in fact, when you try to accelerate something on a GPU, many people try to create something that is on an algorithm that is co-designed for GPUs, meaning that the algorithm itself is going to be a little bit different from the BWMAP or Minimap 2, because those two algorithms are not built for GPUs. And if you dig into what they're doing, many of the design choices are neither for performance nor the accuracy itself, but just tuned for the CPU behavior itself. So over time, people built many things tailored for GPUs, especially with different algorithms. WFA GPUs, Genesis GPU, and actually Logan from this group right here is one of them. And they're all good, but well, when I talk to people on the field, well, they're actually really reluctant to move on to those algorithms directly. And this is not for the accuracy nor for the performance, but primarily because they're just used to the old tools they have been using, and they do not really want to change anything that they don't understand very well. So because of that, our goal is to port something that directly reflects the behavior of what they're using, but just running on the GPUs to be faster. And I want it to be end-to-end, such that what they're going to do is they have a CPU running BWMAP or Minimap 2, and what I want them to do is buy a couple of GPUs, plug it into the system, press the return key, and it's going to run all the same end-to-end. And I don't think this is necessarily the optimal solution, but hope this will be a bridge getting towards a better one in the future. So that's what I have done. Our goal was to build an open source GPU ported algorithm for BWMAP and Minimap 2. So I hope this will place more GPUs in the genomics infrastructure in the field. And because we open source that, this will allow easy modification if there's anything needed. And I believe this is an essential incremental step towards better hardware-friendly algorithms. So our effort for the past 5 years yielded 3 papers, IPDPS, PPAP, and ICS, and that's what I'm going to cover. So this is more like tuning for GPU performance. I'm not really sure everyone here, well, offline or online are familiar with GPU performance. But basically, in classic ways, we talk about 4 things in tuning for GPU performance. First, using a massive amount of parallelism in GPU, you have to worry about what to parallelize and how. First of all, you have specific for NVIDIA GPUs, you have exactly 32 threads work. And then you use many of those works to occupy about in the ballpark of hundreds streaming multiprocessors. And that's really a lot of parallelism, which is not always easy to populate. And then you also have a shared memory, which is a form of scratchpad SRAM. And that is used to capture temporal locality, but they have to be manually managed. Unlike GPU cache or CPU caches, you have to be explicit on which data goes where in this specific memory. And then there's coalescing, which captures spatial locality, which means if you have multiple threads, all the memory loads that has been issued in the same cycle better go into sequential accesses. If they are skewed into multiple cycles or different steps, they will not be coalesced, resulting in many unnecessary memory reads. And then finally, you also want to consider load balancing between works or streaming multiprocessors, because otherwise, whatever is going to end the latest will dominate your execution time. So those were what we were considering on our work, actually for most of the other GPU works. So in the remainder of the talk, I will talk a little bit about background and our core techniques on the 3P papers. All right, so this sequence alignment at its core is approximate string match. Say that we have a reference whose string goes G, A, T, C, and G. And when we read something out of a sequencer, well, there can be a mutation because we are all different individuals. Maybe maybe a base pair was missing, or sometimes a machine error happens. So this might change your A literal into C. So after a mutation or machine error, you get a read that is different from many reasons from the reference. Now, to figure out which reads goes to where in the reference, we need to perform an approximate string match. And that turns out to be a kind of dynamic problem. And because we have to define how similar that is, we want that to be a score-based alignment. So where each time you find a match, we get some plus score, and each time there's a mismatch, we get some negative score, and each time there's an insertion or deletion due to a mutation, we get another part of non-negative score. So there can be many alignments from our initial reference. We can try to match as many as possible with some insertions from the reference. So in this case, we get some pluses for matching, and we get some minuses for gaps. And then on another alignment, we get more matching, but then we have a little bit of a negative for having a gap. And after all, because the score on the right one is larger than what's on the left, we choose this one as our best match. And figuring out is actually difficult, but it's known to be solvable through a dynamic programming. So for example, if we have two strings, GC and GAC, our goal is to find the maximum max score between those two. And what we do with dynamic programming is that we assume that those two will match, and then that's going to leave us a sub-problem of finding a max score on the remaining shorter strings. Or we can just assume that they are causing a gap either on an insertion and a deletion, which will cause, in this case, negative scores, but then again, leaving us with a sub-problem on shorter strings on either side. So that all results in a two-dimensional matrix score. So this is a score we want to get, and that's going to give us a gap from the left side or the top. And then on the match, we will get a plus score from the diagonal. So that all happens, and our job is to choose the maximum between those three. And in this case, we know that our best score is going to be from 2, because we got a +2 score, which is going to be larger than paying the gap penalty from either from the top or the left. And that's what we do for filling the entire score matrix. And after that is done, we kind of know where the max score alignment came from. And from that, we are able to reconstruct which path we have to follow towards getting the best score. And that actually happens in 2 phases. Which one is a forward phase, where we just fill the scores in the direction matrices, which is actually much larger than that. And once we find the maximum score, we go for a traceback. And in which we just find out which path we have to follow through gaps or matches or mismatches that led to our best score. So those two are both important. And for the forward phase, it's usually known to have an anti-diagonal parallelism, which I will visit later. So yeah, but basically, if we want to apply parallelism, we can usually compute all of those and that anti-diagonal directional cells in kind of independently. Yeah, and usually the problem is that both the reads and the references are pretty large, which is both computationally and from the memory side very expensive. So for that, usually the commercial tools follow three phases: for seed, chain, and extend. I don't want to go into this very too much deep, but usually we find some exact matches which are called seeds. In this case, AT is found both from the references and the reads, and also CTG is found both from the references and the seeds. And the read, using that as a seed, we found some combination of them considering directions and the distances. So in this case, we find out this as the correct chain in the chain phase. And after that, we finally move on to our dynamic programming phase for filling the empty space between those seeds on forming the chain. And now we go over the same dynamic programming algorithm to find out whether we have a very good matching score to figure out whether really those reads go into this position in the reference. Now, if you want to break down, well, depending on which data set and which application, actually they are all important. Seeding, training, and extending. And our initial plan about 5 years ago was to build a kernel for each of these steps. And we thought we could locate that to build an end-to-end algorithm. And that turned out to be not so simple because that's doable in principle. But if you look at the algorithm, it's really very complicated in the flow. And because of that, it makes me very difficult to explain them all. So I will just focus on the extending part because that was more interesting for us for the sake of GPU acceleration. And for the rest, I think we can use the paper. So when we started working on the extension part, which is a variant of the Smith-Waterman dynamic programming algorithm that I talked about, arguably the state of the art doing that was called Gezel, published in 2019. And the strategy for Gezel was query parallelism. And because there are multiple reads who's providing with multiple queries, we can have multiple score matrices to fill, and we're going to use that for a thread to utilize all the CUDA cores. And indeed, that's going to provide us with a lot of parallels. And that's good for GPUs, because GPUs are built for massive parallelism. So this is an easy and efficient way, but not necessarily for the best performance. And I'm gonna tell you why. So basically, if you dig into it, they define something as a block which fits into 32-byte integers. And the reason for that is each base pair has to occupy 4 bytes. Well, we know that it can be one of A, G, C, and T, which can be only 2 bits. But unfortunately, we have the fifth little, which is for unknown, that comes from the sequencers. So we use 4-byte packing, and that gives us an 8-by-8 block that fits into a single word. So now within a block, using a CUDA thread, a single thread fills in the entire block for the dynamic programming matrix. Once it's done, it's going to move on to the next block. And for that, we have to start from the boundary. And because a block is only 8 base pairs long, we can hold them in our register. However, later when we want to move downward, we cannot fill the entire row in the register. So for that, the kernel uses global memory. And that actually becomes a huge overhead on the memory subsystem. So looking back, this is good for parallelization, but because the threads are all accessing different parts of the memory, this is not being coalesced, and they don't really use shared memory locality. And because of their different sizes, you also suffer from a huge load imbalance. Given that as a motivation, our first work, Saloga, in IPTPS 2022, was utilizing this anti-diagonal parallelism. So this is our parallelism, but doesn't have to be exactly that. Well, there are many ways of exploring that as long as you do not break the dependencies. So if you start from some with threads here and there are available directions. So you can just explore that in many directions. But for example, you cannot reach here because the dependency goes all the way to something that has not been computed yet. So anyway, this was our strategy. Instead of relying solely on pure irregular parallelism, we decided to use intra-pure parallelism. So given that this is a huge score matrix, we are using all 32 threads in an anti-diagonal parallelism to start with. And given that, we're going to move one. So of course, this is the same 8x8 block. We're going to move one block at a time using all 32 threads in our work. Like this. And because of this, we can deliver the result from the block here to another thread using the shared memory of the GPU. Or if you know about the shuffle instructions, you can use that too. But anyway, when a thread is moving to the next block, same to Gazel, you use registers for delivering the boundary information. For moving downward, you use shared memory to deliver that information to the thread that's working on the lower row of the matrix. So that's done. And now one problem is that we still have to store the boundary information such that we can work on the lower region of the matrix. For that, the last thread 32, has to scale that data to the global memory, which is also bad. So looking back, we actually use less global memory access from coalescing. We have less work divergence because we are having all threads in a work in a single query. The accesses are going to coalesce, but this one suffers from a lot of global memory access that is not coalesced. And much more, we suffer from a loss of parallelism on the prologue because we are starting with only one thread here, with more threads joining later, and we start losing number of threads on the epilogue. And so to fix the first one, we propose a lazy scaling such that the thread number 31 doesn't directly write to the global memory, but just keep that in the shared memory for a while until the shared memory is full. So when it's almost full, now we stop making progress here. And instead, now we gather all the threads and let them write into the global memory all together from the shared memory, such that the accesses are now coalesced. And this is actually one of the classic techniques for CUDA. There's a cute name for it, which is called corner turning. I didn't name that, so I don't really know why this is called corner turning, but this is also applicable here. And for mitigating the prologue and epilogue problem, we actually had to split the work a little bit here. So instead of using all 32 threads here, which is going to create a huge prologue and epilogue, we split the work into two subwords, such that they are going to put into different queries. And this time, because we have only 16 threads, we get a smaller prologue and an epilogue. And that actually breaks a little bit on the divergence and workload balance, but this is actually all trade-off between how much epilogue and prologue we want versus how much workload imbalance we're going to endure. So yeah, that's all for the first paper. And compared with all the baselines, we were able to get a pretty decent speed up, or usually about 2x, depending on the data set. And we actually explored what is going to be the best subwork size, and usually it actually depends on the data set, but we concluded that usually a size of 8 provides a right balance in most cases. So that was our first work called Salova. I'm going to skip this. And when we started to, when we moved on to a longer read for the application Minimap 2, we actually learned that there's an important heuristic that we have to handle. And that we actually named as guided sequence alignment, which is not a popular term. In Minimap 2, they call it banding and z-drop. So what they do is instead of filling the entire table, first, they restrict the region to be a few cells from the diagonal, because the analogy is that if you diverge too much from the center, it's probably a bad score anyway. And then another one is that if the score goes rapidly down, that's probably a bad query anyway, so you stop. And how they do it is that they keep a global minimum, then they also keep a anti-diagonal local maximum, in this case, -6. And they compare this anti-diagonal local maximum with the global maximum. And if the difference is too much, they stop. So we call that a termination condition. So this is all good, usually for CPUs. But now the challenge is that you have to keep the local anti-diagonal maximum every time. And this becomes a challenge, especially given our intra-period parallelism we developed for Salova in the first work. So we actually checked that. So this is execution time. So lower is better. And our previous Salova was running about here. And when we naively applied the mentioned guided alignment, it actually caused a huge slowdown because of the maximum tracking and having to consider the band and everything. This was not really good. So about 2x, we were actually expecting speed up because the amount of work is getting slower from having to fill the entire matrix to just this much. But instead, we're getting a slowdown. So that motivated us to have our second work. I'm spending too much time here, so I'm going to only talk about these two. So first, we have to track the local maximum values. And that turns out to be a little bit difficult. So given a block that is handled by a thread, well, now this is our anti-diagonal, and we want the local maximum among all the cells. And that requires inter-thread communication. And inter-thread communication is always expensive, especially if that's reduction. So for that, we also use shared memory and utilize intra-thread reduction as much as possible. So in this case, all the threads are on the same anti-diagonal. So we're going to calculate scores and put that on the shared memory buffer. So this represents the scores from our first anti-diagonal. And when they move, now their scores are going to the second slot on the shared memory. And the third, fourth, and so on. But when they come back to the top, now we realize we are back on the second anti-diagonal. So for that, we now perform reduce only within individual threads. So we didn't make any inter-thread communication, but just they're all working individually on the row. So we can keep going until we get to the last cell of the block. And if you count here, for 4x4 blocks, which is actually 8x8, but for 4x4, we ended up calculating in total 7 anti-diagonals. So at this point, we know that these 4 anti-diagonals until here has been fully produced, so we can get the local maximum. But for these three, well, we still haven't calculated those cells. So now we're going to only calculate these four and let each thread now calculate the local maximum and finally put that into the global buffer. After they're all done, now they're going to put it to the global memory. And once that's done, we have to keep those and move on to the next set of anti-diagonals. So our window or the shared memory buffer starts. We do the same, working on these 7 anti-diagonals. And then after that, we can actually slide the window again. So the window goes like this. So in this example, we actually needed only 12 rows on the shared memory, which is small enough to fit into each shared memory size. And then if we just follow the way we were slicing from the Solova, this is what you get, and this is how our thread is going to progress. It works. But we see that we get even larger column and irregular because the format is a little bit on the opposite. And when they terminate, we actually do not know whether to terminate because we didn't actually calculate these small set of cells. So we have to additionally process these cells, which we call run-ahead processing. So we actually devised a slightly different way of splitting the cells like this, which fits the format of the banded kernel and calculating the local max, but we actually split it horizontally such that they're going to work a little bit friendly towards creating a coalesced read from the GPU memory and also going to the right. So they were all working pretty well. I'm gonna skip two techniques, but then from the CPU version of the extension, we were getting almost 20x speed up, so that's a lot. And from our naively extended one that I showed on the motivation, we were getting about 10x. And from the original method, I am not really sure which should be called a fair comparison, but still we were getting about 3.6x speed up, so that's a lot. And then this is an evaluation study. We proposed 4 techniques for optimization, which I introduced 2, and they were all getting a meaningful amount of speed up towards the maximum speed up we're getting. So at the end, we were actually very enthusiastic about what we got from these 2 works, and thought about translating that micro benchmark speed up into end-to-end aligners. And that actually turned out to be pretty challenging. From the reason I have talked about, we have to worry about seeding, training, and all the heuristics that are only friendly to CPUs. And well, unfortunately, I don't have much to talk about, except that this was painful for many students. But then for the extension, one thing that I think is worth emphasizing is on the trace stack. So for Solova and the Anata work, we didn't even worry about the trace stack. And that's actually a great challenge, because for the trace stack, you usually have to leave trail on the matrix, on where the solution came from, on every single cell we were computing. And then we actually have to consume on n squared complexity on the memory space and the access bandwidth. And that was actually nullifying most of the speed up we were getting for the kernels. And also degrades the parallelism due to the large memory footprint. And what we were actually doing, we just named it greedy trace stack. which is more like a checkpoint. So instead of storing everything on the matrix, we figured out that many of those directions can be recomputed during the traceback. So if we leave the scores in the middle, we can start from the middle for calculating the scores back again and also the directions. So if we do that, we can use the recomputed directions and the scores to find out where we actually came from for the maximum score. So this is how it actually goes. During the forward, we use the algorithm we have talked about to fill the scores like this. But instead of relying on shared memory and the registers, we actually put some of the cells spilled to the global memory in a gridded manner like this. So all the blue ones are residing in the global memory such that we can read it whenever we want. And after we figure out which one becomes the maximum cell, we can start from there and go ahead, start from the beginning, the top left corner of the grid, and recompute everything. So like this. And from there, you follow where we actually came from. So the recomputation is always restricted to the specific grid we are working with. And at this point, we don't even have to recompute everything from the grid because we know that we are starting from here. So we only recompute this purple part. So we make a traceback in the same way. We also only recompute a partial one on the grid that we are working with. And given that this actually goes over a couple thousands of cells, this strategy is actually very effective, meaning that we don't have to store everything, and the amount of recomputation is taking a tiny part of the entire score matrix. So using that, long story short, we have built an end-to-end BWMM and MiniMap2, perfectly working on GPUs. And I think we have verified it well enough such that we are producing 100% compatibility with them. And I really like to test that on the field. Unfortunately, we do not have enough connection with the field. So I'd very much like to try it. So and somebody tell me. But then both on BWMM and Minimap, we saw that almost 2x speed up both over CPU and other GPU baselines that we could scrap from open source and use to kind of assemble an end-to-end library. So this is a split speed up on the seed, chain, and extend. Like you can expect, most of the speed up is coming from the extend. We also get a little bit of speed up on the seed and the training part. So that's going to translate to about 2x speed up overall. And then these are what we could find from the prior art on piecewise or stage-by-stage implementation from other work. And many of those were not providing with the 100% reproducibility. Sometimes due to a compromise on the algorithm for efficiency, sometimes due to on non-complete coverage on the entire set of control flow and so on. Yeah, but I think we are covering them all. So we were able to fully reproduce the details and achieve a lot of speed up using the GPUs. And for the rest, please see the paper for more details. And we also studied that on extending to multi-GPU scalability. We studied up to 4 GPUs, which were getting a near linear speedup. And yeah, that's expected because we are not doing anything fancy, but utilizing a query level parallelism in each stage. Because, for example, we have, say, 4,000 queries. We're just giving each of the 4 GPUs of 1,000 queries. So anything that's stopping from us from having exact speed up, like entirely linear speed up is a potential workload balance. So that's all of the very quick summarization of the papers we have seen, we have published over the sequence alignment, which I really think is an important part of the genomics pipeline. And I think GPU has a huge potential for accelerating them. And in the future, maybe 5 years or 10 years from now on, what I hope for is they use a hardware-friendly algorithm with an FPGA or a GPU-tailored algorithm, which sometimes people say that they can achieve 100,000 or even 10,000 times speeder. But I don't think that can be adopted very quickly in the field due to the conservative nature of the field. So I think our step towards exact porting of those algorithms in the GPUs can be a compromise. And we have presented many optimization towards this goal. And this is actually all GPU classic optimizations using shared memory, coalescing, load balancing, checkpointing, etc. And of course, yeah, the contribution for those papers was how figuring out the structure of the applications and how to apply those classic optimizations in a clever way. And then we also learned that this BWMAP and Minimap 2 has more complicated details, and we have to learn that the hard way. But then anyway, nonetheless, we have completed end-to-end running software, and we have published that on ICS paper last year, and we have open sourced everything. So if you want to run that, please do. If you ever need our support, yeah, we will be more than happy to assist you. And actually, for this, we had a lot of fun working on that. And I don't know what to do next. Maybe we can go in and try to get this one a little bit faster. But then aside from that, I don't really know what to do. So if you have an idea, if you want to make a collaboration with us, yeah, please do not hesitate to contact me. This is my email address. And our lab webpage is ais.snuackr. So that's all. Thank you again for having me, and I will be ready for any questions.
Thanks a lot for the talk, first of all. I have some, as I told you before, I started working on the topic, but it's like 5 years ago, so it's not what I'm working on right now, so I'm not an expert, but I'm curious because when I was doing, I was optimizing on FPGAs, not GPUs, but we were doing kind of a similar approach with the anti-diagonal. And I remember we were leveraging like multiple matrices for the score. I don't think we had a single one, but we had the metrics for the match, metric for the mismatch. Is something you can do or you try to apply, or does it make sense?
Oh yeah, so actually, I believe what we are doing is a little bit similar. So we are not only utilizing the intra-query parallelism, but there are multiple matches that we have to do. So yeah, we do have to use that because the amount of parallelism we can utilize inside the query was only up to about like the 32 threads, which is nothing compared to the entire amount of resource we have on the GPU. Usually GPU has a lot more. And of course, if you want to do that on FPGA, it's likely you have to have a lot more. So yes, you will have to work on multiple, what I call queries or requests. And I don't think that's acceptable. We do have to use that depending on what kind of accelerator you're using. And I don't know what you were doing, but for FPGAs, a popular approach is to use a one-dimensional historic array. Yeah. And I think that's a great way to do so. And when you do that, you will probably have to insert a lot of such one-dimensional historic arrays. And I think the best way of utilizing such historic many historic arrays is to use utilize many of those queries. And luckily, in this for BWMAP and Minimap and their variants, they always come with a lot of queries because a query is just not a single request from a user, but what comes from what comes from multiple of those trains, and there will be so many empty spaces that you will have to fill via this network, this dynamic power algorithms.
And another curiosity I had, like when you're computing the trace, like it's very interesting to say the checkpoint. Isn't it the thing I was thinking is that yeah, when you compute the checkpoint, like as you can see in the top two boxes, you are leaving some empty space like the white blocks because you are not going there. Is it a problem like for the memory that you have varying blocks? How do you handle that? You still load the black box, but then you don't compute because you are like how do you handle that? Isn't it a problem for the memories that you don't have a fixed?
Oh yeah, actually, yeah, that's a very good question. Yeah, we did have a problem on that. Yeah, so yeah, for example, we are not computing this one, and sometimes they are like reducing this much workload doesn't even have that all. Yeah, because yeah, well, the anti-diagonal parallelism goes like this, and many times if you compute this is almost for free because the amount of time you need for computing this will be like totally identical. So sometimes it doesn't help, but given that the blocks are actually much larger, if you can only do this by computing a very small fraction of the if that is, I don't really remember the exact number, but if you have to compute something like more than half, it doesn't really help much. And sometimes I think because of that exact reasons, if we have enough parallelism, we were computing this cell using a single thread, just like the gate cell approach we were doing before, because sometimes we usually have other requests for the parallelism. And in that case, it does help. But we are giving up on the policing and the sharing of stuff. We were claiming for the forward pass.
Okay. Thank you. Yeah, I don't know if there are any other question in case. Thanks a lot. Thanks again for the talk. Now we can have a brief discussion after that. And thanks everyone for participating. We will meet next Friday with another talk from Marcello. So thanks everyone. Have a good day. Thank you.
All right. Thanks for having me.
Thank you. Thank you.
Thank you.